Hello guys, welcome to my second class of vector space. Now we already discussed in the first class what's the definition of vector space, what's the definition of subspace, and also we discussed one result. Means a non-empty set subset W of a vector space is a subspace if and only if it is closed under vector addition and also scalar multiplication. Now moving to the second result. The result is a non-empty subset W is a subspace of a vector space V over a field F if and only if they combine both closed under vector addition and scalar multiplication is nothing but A alpha plus B beta belongs to W for all alpha beta belongs to W for every A B belongs to field. Means scalar. Now, first you have to take first side. Suppose W is a subspace of a vector space over a field F. Now we already discussed in the first result, whenever any non-empty set is a subspace, it is closed under vector addition and also scalar multiplication. Therefore, immediately I am going to take that implies W is closed under vector addition and scalar multiplication. What's the meaning of vector addition and scalar multiplication means? Suppose choose two vectors A alpha and beta in W, then sum is also in W. Suppose choose one alpha vector, alpha belongs to W, scalar C belongs to F, then the product must be in W. I have taken this is star, this is double star. Now, I want to prove A alpha plus B beta belongs to W. Therefore, what I am going to do here, I am going to choose let alpha beta belongs to W. A and B belongs to, A and B not belongs to W, is belongs to F. This belongs to F. Then from the what about scalar multiplication, A alpha belongs to W and B beta belongs to W from double star. Again from single star means closed under vector addition, clearly say that A alpha plus B beta belongs to W. For every AB belongs to F and alpha beta belongs to W. Thus completes one side. Suppose W is a subspace of a vector space over a field F, then A alpha plus B beta belongs to W for every alpha beta belongs to W and AB belongs to F. Moving to the canvas part. Canvas part means here the canvas is actually suppose A alpha B beta belongs to W means for every AB belongs to F and alpha beta belongs to W, then we have to show that W is a subspace of a vector space over a field F. It is enough to show that W is a what actually? It is enough to show that W is a closed under vector addition and also scalar multiplication, because you know that in the first result whenever I have to prove subspace, it is enough to show that that non-empty set is a closed under vector addition and scalar multiplication. Therefore, what I am going to do here, now I am going to choose the values, particular value of the scalar. Let A is equal to 1 and B is equal to 1. Then I am going to substitute these two values here. 1 into alpha plus 1 into beta. What we get? Alpha plus beta belongs to W. For every alpha, beta belongs to W. Therefore, W is a closed under vector addition. And also I have to verify which one actually I have to verify is what about closed under scalar multiplication. Therefore, what I am going to do here, I am going to choose the particular value of B is equal to 0 in 1. What is 1? A 1 is nothing but A alpha plus B beta. A alpha plus 0 into beta, what we get actually A alpha must be belongs to W. For every, since A and B are scalar, therefore it's possible to choose the particular value. That implies A alpha belongs to W for every A is in F and alpha is in W. This shows that W is closed under scalar multiplication. We already proved that closed under vector addition and also scalar multiplication. Therefore, W is a subspace of a vector space over a field F. This completes the proof of the second result. Moving to the third result is one of the important result. The intersection of any two subspaces of a vector space over a field F is also a subspace of a vector space over F. Now, if you want to prove this, first I have to choose two subspaces. Say let S and T be any two subspaces of a vector space over a field F. Then I had to prove that intersection of these two subspaces is also a subspace. Therefore, first you define what about intersection of a set. You already know that how to define intersection of a set. S intersection T means choose any vector that must be common in both S and T. That's a meaning of intersection between two sets. Same meaning here because S and T are must be nothing but what? Non-empty subset. Non-empty subset. Now, see, since S and T are already assumed that subspaces, therefore S is a non-empty and T is non-empty. Therefore, I have to choose common vector. Say identity vector 0 vector belongs to T, same vector belongs to S. Therefore, this 0 vector is in S intersection T. Then we say that S intersection T is a non-empty. Then we have to show that S intersection T is a subspace of vector space over a field F. It is enough to show that S intersection T is closed under vector addition and also scalar multiplication. Now, if first I have to prove that is a closed under which one? What about that closed under vector addition? Therefore, I choose two vectors. Say alpha beta is in S intersection T. That implies alpha beta belongs to S. From the definition of intersection, this alpha beta belongs to T. But since S and T are subspaces, therefore from the definition of subspaces, S and T are closed under vector addition. Therefore, alpha plus beta belongs to S and alpha plus beta also belongs to T. Both have a common thing, therefore alpha plus beta belongs to be in S intersection T. Therefore, that implies S intersection T is a closed under vector addition. Similarly, to prove that closed under scalar multiplication. Therefore, what we are going to do here, I choose one scalar, say C belongs to F, then alpha belongs to S intersection T. From the definition of intersection, alpha belongs to S, alpha belongs to T. But S and T are subspaces. Both S and T are closed under scalar multiplication. Now we have to say that C alpha belongs to S and C alpha belongs to T. Then C alpha is a common in both S and T. Therefore, it belongs to S intersection T. Therefore, C alpha belongs to S intersection T. Therefore, S intersection T is a closed under vector vector addition. Therefore, from 1 and 2 means already derived is a closed under vector addition and also closed under scalar multiplication. Therefore, from 1 and 2 we say that clearly S intersection T is a subspace of a vector space over a field F. This completes the proof of intersection of any two subspaces again is a subspace. Moving to the last result, sum of two subspaces is again a subspace. Means W1, W2 are two subspaces over a vector space over a field F. Then W1 plus W2 is also subspace subspace of a vector space over a field F. Instead of that, they may will give what about that in the form of notation theory. This is notation, this is a theory. Sum of the two subspace of a vector space V of F is a subspace of a vector space over a field F. First you define a sum, what we define in intersection. First I choose W1, W2 be two subspaces of a vector space over a field F. Then how to define how to define what about that how to define our W1 plus W2 is nothing but I choose one vector, say alpha. Alpha is having two terms, alpha 1 plus alpha 2. Alpha 1 belongs to W1, alpha 2 belongs to variant W2. Okay. Now, I'm moving to the thing. First, I have to show that W1 plus W must be a non-empty. Since W1, we already assumed that W1 plus W1 and W2 are subspaces. Definitely both are non-empty. They have a common vector is identity vector is 0 belongs to W1. 0 vector belongs to W2. 0 plus 0 vector is 0 only belongs to W1 plus W2. Then clearly say that what actually W1 plus W2 must be a non-empty. Next we have to prove that Next, we have to prove that W1 plus W2 is also a subspace of a vector space over a field F. It is enough to show that W1 plus W2 is closed under vector addition and also scalar multiplication. We already from the result 1. Not necessary to verify W1 plus W2 itself is a vector space. Yeah. Now I have to choose two vectors, say alpha 1 plus alpha and beta belongs to W1 plus W2, where alpha is alpha 1 plus alpha 2, beta is nothing but beta 1 plus beta 2. From what we define W1 plus W2, first term of alpha 1 beta 1 belongs to W1, alpha 2 beta 2 belongs to W2. Since we already assume that W1 W2 are subspaces, then that implies that W1 W2 itself is a closed under vector addition. Therefore, alpha 1 and beta 1 belongs to W1 means sum also belongs to W1. Alpha 2 and beta 2 belongs to W2 means sum is also belongs to W2. That is a closed under vector addition since W1 W2 are subspaces. That implies what actually alpha 1 plus beta 1 belongs to W1, alpha 2. Take that sum, what happen, alpha 1 plus alpha 2 group together and group beta 1 and beta 2 together. What we get, alpha 1 plus alpha 2 is alpha, beta 1 plus beta 2 is nothing but beta. Therefore, W alpha plus beta belongs to W1 plus W2. Please try to understand. I am going to repeat once again this part. Which part actually? Alpha 1 beta 1 belongs to W2. Alpha 2 plus beta 2 belongs to W2. Take that sum. Group alpha 1 plus alpha 2, group beta 1 plus beta 2. From what we define, alpha 1 plus alpha 2 is the alpha, beta 1 plus beta 2 is equal to beta. What about the beta? Then clearly say that alpha 1 plus beta belongs to W1 plus W2. Therefore, W1 plus W2 is closed under vector addition. Similarly, I have to show that is a scalar multiplication. Now, how to show that is a scalar multiplication? Now, I choose one of the vectors, say alpha belongs to W1 plus W2 and one of the scalars, say C belongs to F. Then, alpha is nothing but what, alpha 1 plus alpha 2, where alpha 1 belongs to W1 and alpha 2 belongs to W2. You already know that in closed under vector addition. Since W1 W2 itself is a subspaces, therefore both are closed under scalar multiplication. They clearly say that C into alpha 1 belongs to W1, C into alpha 2 belongs to W2. Now I have to take C into alpha. C into alpha is nothing but what? C into alpha 1 plus C into alpha 2. That is nothing but belongs to W1 plus W2. Now you say that W1 plus W2 is closed under closed under scalar multiplication. Now, we already derived closed under vector addition and closed under scalar multiplication. From what about first result, we clearly say that, confidently say that W1 plus W2 is a subspace of a vector space over a field F. This is a way to prove that sum of two subspaces is also a subspaces. We already discussed intersection of two subspaces is also a subspaces. Yeah, I covered some important results in my class. I'll come and meet you in the next class, some more concepts. Thank you very much for listening. Thank you. Bye.